Okay, hi. To start today, I'd like you to have a go at these two questions. These are from old C1 papers, and in these papers, you weren't allowed to use a calculator. So the question's been designed so you don't use a calculator. Have a go, please. Pause the video now. All right, well done. Okay, let's see how you did. So I'm just gonna put the answer up to the first one. You should have got x less than minus 8, 1 8 of 1 over 8, and the second one you should have got 0 less than or equal to x less than or equal to 5. If you got that and you're really happy with this starter, you don't have to watch my explanation of it. Second one, you should have got the following coordinates: x is 3 and y is 12, or x is minus 3 and minus 12. Again, if you got that as the answer, and you're confident, just move on. Otherwise, keep watching. I'm going to explain where these answers came from. Okay, so first one is just what we call a linear inequality. And what do you do to this? Well, there's two ways you could deal with this. Sometimes you get sort of told to make the get rid of that minus 8x, so you might add it to both sides, like so, and then you might minus your 4, and then divide by 8. And so we've got 1/8 is greater than x, or x is less than minus 1 over 8. Okay, all good. Second way you might have done it would be to minus the 3 first of all. So give you minus 8x less than, greater than 1, and then divide through by minus 8. The only thing we then need to remember is to flip the sign. We talked about why you have to do that. This way is much quicker, but I just wanted to talk about both ways so you're happy with them. Okay, linear inequalities sorted. Second one, it's a bit of work to be done with this one. You should immediately sort of see it's going to be it looks like it's a quadratic inequality because we're going to get an x squared coming out of it. So the first things to do is going to be to multiply out our brackets. Okay, there's no way of solving it without multiplying by the brackets. Like the method is always get everything on one side, 0 on the other side, and then we've got methods for how to deal with that. So multiplying it out, 2x squared minus 6x, then minus 4x plus 12 is less than or equal to 12. Okay, let's tidy this up. You can immediately see that you can subtract 12 from both sides, and that's going to go. So that's making the question a little bit nicer. You don't have to deal with a constant in there. 2x squared minus 10x is less than or equal to 0. Okay, what I'd probably do at this point, you don't have to, is because it's got 0 on one side, you can just divide everything through by 2. There's a common factor of 2. X squared minus 5x less than or equal to 0. We're on our way. We just factorize it now. Always the method for how to deal with quadratics. X bracket x minus 5 less than or equal to 0. And what I always teach is to do a little sketch of y equals this thing on the left. It's going to have roots of 0 and 5. It's going to look a bit like this. Where is the graph less than or equal to 0? It's this region here. Okay, and so I can safely say that it's going to be 0 less than or equal to x less than or equal to 5. When C1 was happening, they didn't have interval notation in there, but you can use it if you like, and it would be 0. Oh, I've made a mistake. Let's just get rid of that. It'd be a square bracket 0, comma 5. That means the same thing. Just make sure you're aware of both. Okay, good. Second question, if you weren't happy with it. This is a 10 marker right at the end of a C1 paper, and it requires a little bit more of what's going on. You have to sort of figure out what does the question want, how do we go about attacking it. The first thing we might do, just from experience, like get a little picture of what's going on. Cubics look a bit like this. I mean, we don't know for sure that this cubic looks like that. We've got some sort of line going on. Oh, actually, before I jump into that, it says find the coordinates of the points on the curve at which the tangent is parallel to the line. So I've got a line over here, and then I might have a tangent, say here, that's parallel, and I want to know the points on the curve. So I'm basically trying to find this point here where the tangent is. But there's also going to be another tangent, say here, that's parallel to it. So we might not necessarily get two solutions because we don't know what the cubic actually looks like, but you might. Yeah, so that's just something to be aware of from the start. Drawing a picture can really help with that. And also it helps us sort of think of how we're going to do this, because we've got a tangent. What's the gradient of the tangent? It's 8. Okay, that's the key information we have. Actually, this +3 is no help at all in the question whatsoever. So we're interested in where on the curve the gradient is 8, and that involves differentiating. So we're going to do dy by dx. That's going to equal, I'm going to multiply by the power. 3 times the third just gives me 1, so it's going to become x squared. And then, okay, I should have just prepared this a little bit more. This is 9x to the minus 1, so I'm going to bring the power down, subtract 1 from the power. Okay, we've got quite an awkward thing. And then we're interested in where it equals 8. So I'm just going to put equals 8 here. Okay, this you might recognize. It's going to be a hidden quadratic. We've got a squared, we've got a -2, we've got an 8. So we're going to need to deal with that. We're going to multiply through by x squared first of all to get rid of this -2. So x to the 4 minus 9 equals 8x squared. This is more clearly now a hidden quadratic. X to the 4 minus 8x squared minus 9 equals 0. Being a non-calculator paper, I would expect this to factorize, and it does. You can either use a substitution, y equals x squared, or you can just go straight for it and factorize it in terms of x squared. X squared minus 9, x squared plus 1 equals 0. Yeah, you can see it's not going to be 3 and minus 3. It's got to be minus 9 and 1 to get my minus 8 when I add these two together. Okay, solutions. X squared equals 9, or x squared equals minus 1. But oh dear, we can't have that. We're going to reject this one here. So we're nearly there. We've got that x equals 3 or minus 3. Let's just look back at the question all the way up here. It said find the coordinates, so we're going to have to do that. So I'm just going to need my original equation. Just bringing down now. Okay, and we're going to substitute in for that. So it's going to be 3 cubed, that's 27. Divide by a third, that's 9. And then we're going to plus 9 over 3, that's going to be 3. So it's going to be 9 plus 3, it's going to be 12. Similarly, with the minus, we're going to get minus 27. We're going to divide it by 3. We're going to get minus 9. Then we're going to do 9 divided by minus 3. That's going to give minus 3. So it's going to be plus minus 3. Minus 3. I'm going to get minus 12. Now, I probably would just write this as coordinates to end with. So 3, 12, or minus 3, 12. Okay, 2 questions from topics a little while ago that are worth doing. Hopefully you're happy with those, especially after my explanation. Good. Hi, a second lesson on integration. So we have introduced the idea of integration. as the opposite of differentiation. We've not given any applications of it so far, so today is just the starting point of that. First thing I'd like you to do is write down the answer to this. Okay, so just pause the video and have a go. Alright, what you should get is, I need to write it down here for enough space, is we add 1 to the power and we divide by this new power. Okay, so if you wrote that down, give yourself 1 mark. That's not it though, is it? You need to always add this C. That's your second mark. Okay, now did you get all 3 marks? The third mark is to remember that this is only true for n not equal to -1. Hopefully you remember that. Okay, so today we're going to be applying integration. We've got some situations with functions and so forth, but they might be physical situations. They might still, as this first example shows, just be a graph, but there's a bit more to it, just a little bit more to it than previously. Because this time we've got the derivative, it's f dash x equals 6x squared minus 5x. They want us to find f of x, that's the same as before, but they are telling us that it's going through 2, 3. Okay, so if we want to work out f of x, it is going to be the integral of 6x squared minus 5x. Note, I am putting a bracket around the whole thing that's being integrated. That's just good practice. If you don't put it in, you're being a bit sloppy. Sort of, you can get away with it, but it's best to be, careful, I'd say, or mathematically precise. Okay, we do our normal thing. We raise the power, x to the 3. We divide by that. It's going to become 2x to the cubed. And then we raise the power, this x, that's going to become a squared. We're going to divide by that. We're going to get 5 over 2 x squared. And then we're going to get plus c. But this time, we've got a coordinate. So I guess what I want you to think about is like I might have x squared. Sorry, x squared is down here. I might have x squared plus 1. I might have y equals x squared minus 3. For a given value of x, they've all got the same gradients. That's why if I integrate 2x and I get x squared, y equals x squared, but I get y equals x squared plus c, that's me saying that the gradient 2x would always give me a graph y equals x squared plus c, and I basically get an infinite number of solutions with these plus c's. Right, what is this 2, 3 doing? That is pinning down the graph that I actually want, okay? Because if 2, 3 is on the curve and it's, say, there, well, none of the rest of them go through it at that point. So this extra point allows me to work out c. That's basically what I'm saying here. I'm just trying to give a graphical picture of what's going on. Okay, so we can just substitute in. We can substitute in x equals 2 and y equals 3. Now y is going to be what I replace this by. So I'm going to get 3 equals 2 times 2 cubed minus 5 over 2 times 2 squared plus c. And actually, when you first learnt y equals mx plus c back in the day, you probably did something very similar with that. You find the gradients and then you substitute in an x and a y and you work out the intercept. It's the same thing here really, because c is the intercept. Okay, we're going to need to sort this out. We're going to get 3 equals 2 times 2 cubed. 3 equals 16 plus 5 over 2 divided times by 4. That works out to be 10. Oh, it's going to be minus 10 plus c. And then we're going to get 3 equals 6 plus c. So c is going to be minus 3. And the only thing I need to do, and I've taken up more space than I thought I would, I'll move it down, is I need to write down my final answer, that f of x is 2x cubed minus 5 over 2x minus 3. No c in the final answer because we've actually calculated what it is. Good. Okay, one more example. This is now sort of a physical situation. And this is just starting to hopefully kind of tell you why integration is really useful. The rate of change of a population is how a population changes with time. So it's going to be dp by dt. And let's imagine we knew what that was. We didn't know what the population was, but we knew a differential equation for it. We can then work out the population, and that's basically what theoretical physics is. Theoretical physics consists of loads of differential equations that people then want to solve. There are differential equations for electromagnetism. There are differential equations for force and motion. There are differential equations for quantum mechanics. There are differential equations for fluid dynamics, how water flows or other fluids. There are differential equations for air resistance. Basically, physics is underpinned by differential equations that we want to solve. Once we solve them, we've got the solution, we can understand air pressure, we can understand how the planets go around the sun, we can understand how atoms behave. It's amazing, basically. And it all comes from being able to integrate and solve differential equations. We are going to look at more complicated differential equations as we go on this course. They're going to get more complicated than this, but this is our starting point. So back to the question. We've got the rate of change of population, and it's this. Find the difference in population between year 1 and year 3. Okay, so how are we going to do this? Well, the first thing we're going to do is we're going to integrate. I know the derivative. To get back, I'm going to integrate the derivative to give me p. This time, I don't have y and x, I've got p, and I'm going to be integrating with respect to t. So I've got this dt here. Again, not really spoken about this notation, why we're using it, but it's become our notation for integration. Okay, next bit. Raise the power by 1, divide by it. Raise the power by 1, divide by it. A third t cubed plus t squared plus c. Find the difference in population between year 1 and year 3. So let's say t is number of years. When t is 1, p is going to be a third times 1 cubed, which is just 1, plus 1 squared, which is just 1, plus c. So I'm going to get 4 over 3 plus c. I don't know what c is. Just going to have to leave it like that. And then we've got year 3. T is equal to 3. It's going to be a third times 3 cubed. That's 27. So it's going to be a third of 27, which is 9. Plus 3 squared, which is also 9. Plus c, which is 18 plus c. Okay, and now let's just remember we are interested in the difference. So we're going to subtract them. Difference is going to equal 18 plus c. That's going to be the larger one. Minus 4 over 3 plus c. I'm doing this maybe overly careful. You might just be able to see that the c's cancel, but I'm just going to take my time with my brackets. Minus 4 over 3 minus c, and the c's in fact cancel. I'm left to work out 18 minus 4 over 3, which is going to be 16 and 2/3. let's just look back at the question. It said, find the difference in population. It does say the population is in millions, so just to finish it off, I'd probably say 16 2/3 million. I might round it 16.7 million. Okay, and that's it. So we can now use integration to find more, to also apply it to these situations, find the values of C, or in some cases we're not interested what the value of C is, find the difference between things. So have a go at some questions. We're gonna keep going. Next time we're gonna look at something quite amazing that integration has to offer, but I'm not gonna spoil it. You'll find out soon. Thank you for watching.